So let us start the lesson today. So if you remember, we talked about equations of this form in complex numbers. Z to some power n equals to w. Z and w belong to the set of complex numbers, and n is an integer. Okay, so of course we consider the natural numbers. So there is no big distinction between -1 and +1s, because even, for example, if you have z to power -3 and you want to solve that, you write it in the reciprocal form and write z to the power of 3 is equal to 1 over w, and then you can call this capital W. Yes? So in principle, it doesn't matter if this number is negative. So you can safely work with positive numbers. Okay, so let me give you some examples to refresh your memory and then complete the lesson. Okay. So, for example, let us solve this equation. Solve 2z to the power of 5 equals to 1 plus square root of 3i. Okay, so we want to solve this equation. What we do first, actually, what is your opinion? What should I do first? Yes? Divide by 2 to make it in the standard form. So I divide this by 2, so then I get z to the power of 5 is 1 over 2 plus square root of 3 divided by 2 times I. And then you remember, what should I do? I am looking for this z, and then I will ask you to, I would say that let the z that I am looking has this polar form, r cosine theta plus I sine theta. Yes? Of course, here this means that r is missing, theta is missing. But what pieces of information do I have regarding r? I know that r is a number which is real and is positive, yes? So because this is absolute value of z, and clearly z cannot be 0, because if I plug 0, the left-hand side becomes 0, the right-hand side is not equal to 0, so definitely z equal to 0 is not a root. So this absolute value is definitely not equal to 0, and absolute value has to be positive. So what I know here is that r is greater than 0, and of course I know that r is real. But which value is that? We don't know. Which value theta is? We don't know yet, yes? So what I need to do, I need to use the Denwar's formula and then raise it to power 5 and plug it back into my equation. So z to the power of 5 becomes equal to r to the power of 5, do you remember? And then instead of raising it to power 5, because of the Denwar's formula, I can just simply multiply the argument by 5. And I get this. And then when I plug it into this equation, what will happen? I will have r to the 5 cosine theta plus I sine theta, yes? Oh, sorry. Cosine 5 theta plus I sine 5 theta is equal to this number. It's 1 over 2 plus square root of 3 divided by 2 times. Okay, do you remember what was the next step? Don't forget, your goal is to determine r and theta, because if I find because you see that if I find r and theta and plug it back here, then I will find my z, and that's my goal. I want to find z. Yes?
Should we not compute the theta of the right-hand side?
Pardon?
If we rewrite I over 2 plus the square root of 3 over 2i, so that it's in the theta, in the other form.
In the polar form,
yeah. The polar, yeah.
Yeah, that's possible, but that is not what I followed, yes? I followed, of course you are right, you can write this in the polar form and compare them, but then you will face actually an equation with 2 unknowns. There's 2 equations, 2 unknowns. It is doable, of course, But I prefer to use absolute value. I'm saying that the left-hand side is a complex number. The right-hand side is also a complex number. If two complex numbers are equal, definitely the absolute value of this one should be equal to the absolute value of that one. But can I go, okay, let me ask you, what is the absolute value of this guy?
R to the 5.
R to the 5, yes? So the absolute value of this one is R to the 5. Absolute value of this guy is actually this number, 1 over 2 to the power of 2 plus the square root of 3 to the power over 2 to the power of 2. And if I simplify this number becomes 1 over 4, this number becomes 3 over 4, and this is 4 over 4, which is 1. So I have to calculate R to the 5 equals to 1. So it is, but be careful, I am not solving it in the set of complex numbers because R is a real number. So what you'll have learned about real numbers is applicable immediately here. So I am looking for a real number, a positive real number whose fifth power is equal to 1. There's only one of those numbers, yes, and that number is 1. Yes? And then I plug this back into this equation. Of course, this is so simple that if I plug back this in this equation, I am done because 1 to the power of 5 is just 1. So I put this back into this equation. Then I get this. I get cosine 5 theta plus I sine 5 theta is equal to 1 over 2 plus the third square root of 3 divided by 2 times I. Okay, so one of these questions I was able to answer actually. Okay, and then you compare the left-hand side with the right-hand side. If two complex numbers are equal, then the real parts and the imaginary parts should match. Yes, so this will give rise to this equation that a system, 2 equations, but only one unknown, not 2 unknowns, because the only unknown left for me is theta. So the real part should match with the real part, the imaginary part should match with the imaginary part. Okay, and then I don't know if you remember these numbers, these are famous in trigonometry, yes? So I want an angle whose cosine is 1/2. And if I just tell you, give me an angle whose cosine is 1/2, then it would be a little bit problematic because there are 2 main angles, yes? One angle would be 60 degrees and the other angle would be in the 4th quadrant, yes? But this is why we also need this one. Because if I go to the 4th quadrant, then sine becomes negative. When you say that sine is positive, it is forcing that this angle 5 theta should be in the 1st quadrant, and that becomes unique. Yes. So do you remember what is this angle? So there's only one angle, main angle with this property, and that is 5 theta. It is 60 degrees, which is pi over 3. But of course, you know that you need to write 2. Let me here write k. K 2 times k pi. And then k belongs to the set of integers. But I am looking for theta. So theta becomes what? It is 5 pi over 15 plus 2k pi divided by 5. So this is my k. In principle, how many answers I got for theta? Infinitely many answers. Okay? But my point is actually not finding theta. I need theta because I need z. Yes? So in principle, I should put that theta in this equation and then I will find z. But do you think that because I have infinitely many thetas, it will give rise to infinitely many z's for the answer?
No.
No. Why?
They all have the same endpoint.
They will start repeating themselves after a while, yes? So even though I have infinitely many thetas, all of them are okay, But if I plug them back into this equation to find z, I will get infinitely many forms for z. But they will fall into 5 categories. You will see. And then this is crucial. If you have 5, it would be 5. And I told you a rule of thumb. If this happens, and if you want to solve that equation, you need to only consider k equals to 0, 1, 2, 3, up to 1 unit less. Yes, that's a rule of thumb. Of course, I want you to understand that. After understanding that, you can use this rule of thumb. And the reason is that, for example, if I put theta k equals to 0, what I get theta is equal to pi over 15. And then if I put k equals to 1, I get theta is equal to pi over 15 plus 2 pi over 5. If I take the common denominator here, 7 pi. And then if I put k equals to 2, so theta becomes pi over 15 plus 4 pi over 5. And then it becomes 13 pi over 15. Yes. And then if I put k equals to 3, then I will get theta is equal to pi over 15 plus 6 pi over 5. Yes. Yes. 0, 2, 4, 5. And then if I calculate, it becomes 19 pi over 15. And finally, when I put k equals to 4, theta becomes pi over 15 plus 8 pi over 5. And if I calculate this, it becomes 25 pi. And of course, here I can simplify it by 5. So it becomes 5 pi over 3. I think it's better to keep it in this way to see the pattern. Yes. And then, of course, if I give k equal to 5, that would be a new angle. But the final point of that new angle corresponding to k equals to 5 would be exactly pi over 15. Can you say why? For example, if I put k equals to 5, what happens? If I put 5 there, it becomes this, 15. Theta becomes that. And if I put 5 here, you see 5 and that 5 will be cancelled. So I will have my original angle plus 2 pi more. But that's just one unit circle, just one full circle. So it means that I am just going back to the same angle. And not the same angle, but I go to the same final point. And what matters for me are cosine and sine. So if I return to the same point, regardless of the value of the angle, cosine and sine are the same, so it will give rise to the same value for z. Yes, understandable? Okay, so we stop here, but we have to calculate z. How many roots do I have? 5. z1, z2, z3, z4, and z5. So these are 5 possible answers for that simple equation. Yes. Okay, let me write one or two of them. So r was 1, so don't need to bother about that. So it becomes cosine of pi over 15 plus I sine pi over 15. And then the other answer, I put r equals to 1, so that's the same. But then cosine, the next angle is 7 pi over 15 plus I sine pi 7 pi over 15, and then you can continue on writing. Yes, but you can also write it in a more compact form. Yes, you can write z sub k is equal to the cosine, and then you put this angle inside. Yes, so let me write it properly here. So if you want to write it in a compact form, if you really don't need all of them in detail, so you can say that the answer to this is z sub k is equal to the cosine of pi over 15 plus 2k pi over 15. Yes, plus I sine pi over 15 plus 2k pi over 15. And then you write in front that k is either 0, 1, 2, 3, or 4. So that's also a good way of writing, especially if you really don't need to do something with a particular solution, this is a good way to write that down. Yes, but if you don't write this, it's not complete. It's not good, because then people might think that you have a lot of options, but you have only 5 roots. Yes, 1 corresponds to 0, 1 up to 4. Is that understandable? Yes. Good. Okay, so now and by the way, this is also good from geometrical point of view. It's good to understand where the roots lie on the complex plane. It's important, by the way. So what we do, and so can you tell me where these points lie? If you want to see where these points lie, let us consider the absolute value of zk. Can you tell me what is absolute value of zk? For k equal to 0, 1, 2, up to 4? Yes? Yes?
1.
It's 1. Yes? So all of them has the distance equal to 1 from the origin. So all of them in this case lie on the unit circle. This is the unit circle. The reason that it is unit, it's coincidence, because the absolute value is 1. If the absolute value is 2, this circle should be a radius 2. Okay, so that's, be careful. So the unit circle, and then one of them is corresponding here. So it's pi over 15. I don't know, pi over 15 is how much? I don't know. So let us consider this one. But for example, assume that this is pi over 15, 180 divided by 15, yes? So it is 12, yes? 12 degrees. So it is probably smaller than this one. But anyway, that's 12 degrees. And then you add, the other angle is 7 pi over 15. So 7 pi, it is 12 degrees. So it becomes 84 degrees. But 12 degrees, 84 degrees, how much we increased? So I don't know. So you need to increase it exactly with that number. So 2 pi over 5. So let us consider every time what I am adding 2 pi over 5. Yes, 2 pi over 5, 2 pi over 5, 2 pi over 5. And then what is 2 pi over 5, by the way? If you have a pentagon, so if I have a regular pentagon, and then if you find the center of that pentagon, and then you so you just connect these. Okay, can you tell me what each of one of these angles are? What is the size of each one of these angles? It's 2 pi over 5. Yes, the whole angle is 2 pi divided by 5. So it's clear. I start from here. Every time I am adding a 2 pi over 5. Do you see? 2 pi over 5, another 2 pi over 5, it becomes 4 pi over 5. Another 2 pi over 5, another 2 pi over 5. So I am just rotating by 2 pi over 5 each time. So yeah, regardless, it's hard to draw them. What is 2 pi over 5, by the way? So pi over 5, so it is 72 degrees. So each time I am adding 72 degrees. So might be the drawing is a little bit hard for me, I don't know. But this should be a regular pentagon. So so you need to find these vertices. Yeah, it was easier to do it with GeoGebra. So 1, 2, 3, and then probably 4, and then finally 5. Don't rely on my picture at all. But that would be a pentagon. But it should be a regular pentagon. So you start, but you don't start from here. Sometimes you start from here. Here we start from here. That's also a good idea, by the way. If you want to solve this problem geometrically, you just find one of them. Okay, if you can find, and then you don't need to find the other ones, because you know that there should be 5, and they should be on the irregular pentagon. So you can start calculating this angle and start rotating that with that angle. You get the other ones. Yes? Okay, so that's important to understand. So don't trust this picture. You need to understand it yourself. But this is always the case. So if you find the points corresponding to those complex roots, and if you connect them, you will get a regular n-gon. And what is n? N is exactly this number that you get here. Yes? Is that understandable? Okay, so let us now talk a little bit about a famous solution problem, and these are called the nth roots of unity. Okay, so let us. This is not something hard. It's actually simpler than these problems, but I want you to draw your attention to this problem. So assume that n is a natural number. Okay, and I ask you to solve this equation. Z to the power of n equals to 1. Yes? If I am working in the set of real numbers, what would be the solution to this equation? Assume that for the moment that I am working in the set of real numbers, then what would be your answer for Z?
1.
It depends. Yes?
If n is even, then you're allowed to use it.
Then we have two solutions, plus and minus 1. But if n is odd, we have only one solution. Yes? But here, how many solutions do you guess if I extend to the complex numbers now?
N number.
Always n. Always n. Because if you go to the set of complex numbers, an equation of this form has exactly n roots, regardless of if it is even or odd. Okay? But let us discover them. So how we discover them? We would say that let us consider that Z is equal to R cosine theta plus I sine theta. Yes? And then I put it back into this equation, so it becomes R to the n cosine n theta plus I sine n theta is equal to 1. Then I consider the complex numbers, the absolute value. The absolute value of the number on the left is R to the n. The absolute value of the number on the right is 1. Okay, now can you tell me what is the answer here? R to the n is equal to 1. Yes?
It's a real number.
Of what's that number?
And therefore it has to be 1 or minus 1. If
No,
It's just 1.
it's just 1 because R is absolute value. Absolute value cannot be negative, yes? So R is real, R is positive, so it means that R is exactly equal to 1. And I plug it back into this equation. So 1 to the power of n is just 1, so it becomes cosine n theta plus sine n theta equals to 1. And of course, you realize that cosine n theta should be the real part, which is 1, but sine n theta should be the imaginary part, which is 0. Because 1 can be assumed to be written in this form, yes? Okay, and then I am looking for an angle, n theta. So the cosine is 1, the sine is 0. So what that angle is, that angle whose cosine is 1 and its sine is 0, is 0. But of course, you know that you need to add any multiple of 2 pi, where k is an integer. And then I am looking for theta, so I have to divide by n, so it becomes 2k pi divided by n. K belongs to 0. But how many of them will give rise to different answers? So where should I run k? So let me just clean this one, because now you understand. By the rule of thumb, I need to only care about which values for k. Can you tell me? Which values of k gives rise to distinct numbers for z? Yes?
0 up to n minus 1.
Yes, so it becomes 0, 1, 2, up to n minus 1. Yes, so that is theta. And then let me write these roots. In complex numbers context, it is common to call it omega k. Okay, so when we say omega k, it means that this is cosine. Then I put this angle inside. Yeah, this is just for simplicity. So these are the roots that you are looking for. And k is 0, 1, 2, up to n minus 1. And what happens if I put k equal to 0? Do you see what happens? If I put k equal to 0, what do I get from my equation? If I put k equal to 0, sine of 0 is completely 0, so this is gone. And cosine of 0 is 1. So it's still one of the roots is exactly 1 as predicted, yes? If I ask you, can you just give me one solution to this equation, immediately you say that z equals to 1. Yes? So z equals to 1 is actually still the same. And then something that I want you to tell, the values that you get, which corresponds to k equals to 0, is called the principal value. Okay? The principal, yeah, with a, principal value. So the one which corresponds to this equal to k equal to 0 has a particular name. We call it the principal value. Okay, let me start telling you something that why polar form is still useful again. Let us solve it in Cartesian coordinates. That's what happens, yes? So, for example, let me give you an example which is doable. At least you can feel the problem. Why using the polar form is very useful when it comes to these kinds of calculations related to the roots and things like that. Okay, so for example, this is also a nice technique to learn, okay? So example, this is a very simple example, so you can solve it. Example, let me write a solve z to the power of, just let me tell you just 2 here, equals to 5, for example. Well, okay, let me make it more interesting here. So 3 plus 4i, and then I want you to see why this trick is very nice. So solve this equation. Yes? So assume that till now I haven't talked about the other method, but let us just naively start calculating this. It's doable, but I want you to see what is the problem there. So what should I do as before? I would say that let z be equal to what? Be equal to r cosine theta plus I sine theta. And then what happens? I put it back into this equation, so then it becomes what? R squared cosine 2 theta plus I sine 2 theta is equal to 3 plus 4i. Then you remember that immediately I compare the absolute values on both sides. So the absolute value on the left is R2. The absolute value on the right is the square root of 3 to the 2 plus 4 to the 2. Yes, is that understandable? So I immediately compare the absolute values. The absolute value of the complex number on the left is R squared. The complex number of this number is this expression. So they have to be equal if they are supposed to be equal. And then this is very simple. This is just 5. R squared is 5. I am looking for R, but I know something. I know that R is real and positive. So R is just a unique number, and that is the square root of 5. You are not allowed to write plus minus square root of 5 because you already know that R is positive. Okay, and then what I have to do you remember? I have to plug this back into this equation. And then what I get here, it becomes 5 cosine 2 theta plus I sine 2 theta. On the right-hand side, I will have 3 plus 4i. But I think it would be easier if I divide by 5 first. So it becomes cosine 2 theta plus I sine 2 theta is equal to 3 over 5 plus 4 over 5i. Now they are easily comparable, yes? Okay, so what can I conclude from here? I can conclude that cosine 2 theta, you see the problem now, 3/5, and then sine 2 theta is 4/5. This is what I get, not more than that. But these are not famous angles, yes? And if you put this in the calculator, you might get a lot of decimal points, yes? So what can I do now if I want to keep the exact values? What can I do? Can you tell me?
You have to use the arc symbol and the arc.
Yeah, but then it's a little bit problematic. Which arc do you want to use, arc sim or arc cosine? At the end, if you do them consistently, it doesn't matter. It will work. And then I want you to see that there is a little bit problem here, yes, because this would be too much for us. For example, let us concentrate. First of all, both of them are positive, so it means that these two theta should be in the first quadrant. And at least this is good at somehow. So what I get, I don't know which one is easier to work. Let us work with arc sine. So this means that 2 theta is arc sine. Okay, I don't know. Let me write sine inverse in the notation in the high school. So it's 4/5. But this is not the only answer, so I need to add 2k pi to it. Yes? And then I divide it by 2. So you see that you are facing a little bit of a calculational problems, yes? Okay? And of course, how many values are there for k? Because here it is the second root. By that rule of thumb, you know that k should be either 0 or 1. So it means that I have 2 values, yes? One of them is k equals to 0, so it gives me 1/2 sine inverse of 4/5, and the other one, theta, if I put 1, it becomes 1/2 sine inverse of 4/5 plus pi. Yes, is that understandable? So, but the problem is that it is not so nice as before, yes? Especially if we can find an alternative way to do it exactly. This is exact value. This is not something wrong, but you need to calculate this. Another idea is to use arc cosine. That's also possible, yes? Instead of using this finding theta, I can use that to find theta. Then the solution would be involved with arc cosine or cosine inverse, yes? But the cosine inverse of that number turns out to be equal to the sine inverse of that number. You can, for example, use your calculator to confirm that. So that is not an inconsistency. Okay, and then you need to plug them back into this equation and find your z. Okay, so for example, so I will have 2 values, z. Let me write z naught for this 0. So r is square root of 5. So you see what's happening. Then I will have cosine of this angle. Yes, plus I sine of that angle. This is your solution. And the other answer is probably, you see that this is z1 is equal to square root of 5. And then what should I write? I should write cosine of 1/2 sine inverse of 4/5 plus pi. And then I will have plus I sine 1/2 sine inverse of 4/5 plus pi. Yeah, it's a little bit strange, but this is completely correct. By the way, can you simplify the second one a little bit more? So this you need to know. This is not something hard for you. What is cosine of this angle? Can I get rid of this pi somehow? So this is an angle, and then I am adding pi to it. So if this is the angle, and I'm adding pi to it, I will go exactly on the opposite side. So if this is x and y, this becomes minus x and minus y. Yes? And now I am looking at the cosine of this angle. The cosine of this angle is minus x. So compared to the cosine of this angle, which was x, so they differ by a negative sign. We talked about that before. So the cosine of any angle plus pi is negative of the cosine of that angle. Yes? And that's the same reason, that's the same is for sine. So instead of writing this, I can put this one with a minus sign and this one with a minus sign, and I can factor the minus sign out. If I factor the minus sign out, it becomes minus z naught. Yes? So this becomes negative of this number, this becomes negative of this number. I pull the negative sign out, and then what is left is negative of z naught. So one of the answers is z naught, the other answer is minus z naught. By the way, this is exactly according to your intuition. Do you remember when z squared is something, you want to find z, you write plus and minus. And that's exactly confirming that plus and minus is actually coming through. Okay, but let me give you an alternative here. And of course, it is not something that you can do every time. We have to use the de Moivre's formula. But in this case, because this power is not very high, we can also use Cartesian coordinates. So what do I mean by that? Instead of saying that let z be equal to this and looking for r and theta, I can say that let z be equal to x plus yi. Yes? And then I am looking for x and y. Now you will see what is the downside. But for this case, it becomes better. Because if I consider this, then what do I need to do? Can you tell me what would be the next step? Yes?
Expand it.
Yeah, put it back into the equation and expand it. Yes? So here, I put it back into this equation. So this becomes x plus yi to the power of 2 is equal to 3 plus 4i. And then I can easily expand that. And that is the problem. If this was 3, expansion is harder. If this is 4, expansion is harder. But that is not the only problem. You will see why. Not only expansion becomes harder, but the equations involved becomes formidable. You will see. So if I raise it to power 2, the first one to the 2 is x squared, 2 times the first one times the second one. And the second one to power 2 is minus y squared, yes? And then I will have 3 plus 4i. So let me arrange them. So it becomes the real part is x squared minus y squared, and the imaginary part is 2xy multiplied by I, which is equal to 3 plus 4i. Yes? Now, it is manageable here. Because on the left-hand side, I have a complex number. On the right-hand side, I have a complex number. They are supposed to be equal. So this can happen only if x squared minus y squared is 3 and 2xy is equal to 4. Yes? Is that understandable? And then if I ask you, can you solve this system? Probably yes. It's not a very hard system. But be careful. If I increase it from 2 to 3, first of all, expansion becomes harder. Because what can I do? I have, at most, I can use the binomial theorem. But binomial theorem for large values of this power becomes very big. But most importantly is that when I write it in this form, it becomes a complicated expression in terms of x and y. And when I equate that, I will get a very harder system. You understand what it means? It is a system of 2 equations in 2 unknowns, I agree. But the form of the system becomes much harder. And there is no guarantee if we can solve that. Yes? Because this is at least quadratic, the second power. And we know a lot about quadratic. But assume that when I raise it to power 3, at least you expect the power of 3 appearing here. And method of elimination will give rise to a 3rd degree polynomial equation, which is not in principle easy to solve. Yes? So this is why it is really different method. Don't think that this is just for simplicity. If I have to the power of 5 to the power of 7, then I will get a system involving 7th power of x and y. Even if we manage to eliminate and write an equation, that would be a 7th degree equation, which we don't have any formula for that, how to solve it. So this is, by the way, don't think that this is just for simplicity. No. Not only for simplicity, but this is the only way if we go to high powers. Yes, this I want you to understand. But let us now solve this problem. It is easy. How can I solve this problem? First of all, let me just divide by 2. So what is your suggestion to solve this system? You have everything at the level of your math knowledge to be able to solve this. So how do you want to solve this system? Yes, how do you solve it?
Well, for the second equation, we either have x is 2 and y is 1.
Yeah, method of substitution. This is the most general strategy to tackle any kind of systems. Yes, try to get rid of the extra variables. Okay, and I think that you agree with Sanders that this is easier to eliminate than this one. So let us choose this one. So let us write y equals to 2 over x. But am I sure that I can divide? You have to be sure that x is not equal to 0, but clearly x is not equal to 0. If x is equal to 0, the left-hand side is 0, the right-hand side is 2. So definitely x is not equal to 0, so I am on the safe side, I can divide by. And then I put it back here. I don't want to clean this. Let us see if we can get some conclusions out of it. If I put it back in this equation, then it becomes x squared minus this 1 to power 2 is 4 over x squared is equal to 3. Agree? Yes? Do you agree with me? I put it back in that equation. And then you know how to solve this. What is the first step to solve this? Immediately. Yes, 1, 2, 3, finished. What should I do?
Common denominator.
Common denominator is good, but let us get rid of it by multiplying by x squared. Yes? By multiplying by x squared is x to the 4 minus 4 is equal to 3x squared. And then I move everything to the left. So you see, I am already facing some problems, yes? This is a 4th degree equation. But we are lucky, because if you have done your homework well in Math 2C, you immediately realize how to solve this. This is a 4th degree equation, but how can I solve this? Yes?
We substitute x to the 2
with another variable. Yes, so this is, you see, I want you to see it. We cannot be so lucky all the time, but we can solve it here now. So I would say that let x be equal to t. By the way, what type of numbers are x and y? Are they complex numbers or real numbers?
Real numbers.
Real numbers, because I have written z in this form. Yes, be careful. X and y are not complex, they are real. If I put this back into this equation, then I will get t to the power of 2 minus 3t minus 4 equals to 0. But let me just solve it. Of course, you can use PQ or ABC formula, but the factorization of this is so simple. I need two numbers whose sum is minus 3 and the product is minus 4. What are they? Minus 4 and plus 1. Yes? And then this immediately becomes clear that t is equal to 4 or t is equal to minus 1. Do you think minus 1 is acceptable here?
No.
No. Because I put minus 1 here, x squared is equal to minus 1. Can I say x is I? Or minus I? No, because x is assumed to be real. So this problem, even though I want to solve the whole problem in the set of complex numbers, but don't get confused. This equation is being solved on the set of complex numbers, yes? So then it means that this is not acceptable. Why? Because if I put minus 1 here, x squared, so if t is equal to minus 1, this gives me that x squared is minus 1. But because x is real, this cannot happen. So let me just put this sign for contradiction or whatever. So this cannot happen. But if t is equal to 4, this means that x squared is equal to 4. So what can I get? X is plus or minus 2. Do you agree? Okay, so let me open up a little bit of a space here for myself. Okay, so here I got x is equal to minus 2, x is equal to positive 2. But I need my y. But y is very simple now. Yes, y is 2 divided by x. So if this is the case, what happens? Y is minus 1. If this happens, y is equal to 1. Agree? Which one is simpler now? This number is so simple, yes? So I got my z actually. So what is z? Z is equal to minus 2 minus I. This is one answer. And the other answer, z is 2 plus I. Do you agree? Okay, so which one do you prefer as the answer? This one or that one? But I just want you to feel that. I want you to feel that. The problem is that for this one, this should be in your toolbox. For finding a number to power 2 is equal, might be this method is easier than in general. Yes? But you can try yourself. Solve the same equation for z to the 3. And then see what happens. You have to do these things if you want to learn good. By the way, do you remember I told you something that complex number will help us to understand something in the real numbers? Now we know this number, by the way. Yes, what that number is? We need to compare them. So this one is in the first quadrant. Do you agree? This one is in the third quadrant. This is in the third quadrant. This is in the first quadrant. So it means that this and this should be the same because we are calculating the same thing from 2 different ways. So then if I compare this one with that one, it means that the square root of 5 times this is equal to 2. Yes? So this means that this number that this is not a complex, this is not a problem in complex numbers. Do you agree? It is 2 over square root of 5. So it means that we are using the complex numbers, the ideas coming from complex numbers to calculate something in the real numbers, yes? This is just a problem in trigonometry. So I don't know if you can confirm that using your calculator. So you need to write this minus this. Hopefully this is correct that we have done this one correctly. But you need to punch all of them in one go.
Yes.
Is it 0? Yes.
Yeah.
So that's we calculated something. So, but it is very tricky if someone asks you to calculate this to come up with this solution, solve it in 2 different ways and compare them to get this one. But it doesn't mean that we cannot solve it in the set of real numbers. Can you come up with a solution to this? I told you that you will study these sine inverses in the university, but I think you can solve the problem. It shouldn't be hard. We should be able, that's also good exercise. So let us do that. For example, if I want to do this, I could never understand the connection. This is a coincidence. I have both of them in front of me in the board and I can compare them. But if you give me this to calculate this, I should be very creative to be able to cook up this recipe to compare them, yes? But is there any way that we can calculate that? Okay, so that is also something I wanted to teach you a little bit. This is not hard. So if you start from here, let us consider, of course, if I talk about this angle, it is not that hard. Because when you say sine inverse of 4 over 5, you want to know something about this. Okay, yes?
You draw the unit circle and then you...
No, unit circle is not a good idea here. So here I will take it, for example, x. I am looking for this x. What I do, it means that sine of x is equal to 4 over 5. And then I just go to the right angle triangle, yes? If I have a right angle triangle, do you agree? Because sine x is equal to 4 over 5, so I can consider a right angle triangle whose hypotenuse is equal to 5 and the opposite side is equal to 4. Yeah, so this is not a good picture because that would be this should be smaller. Anyway, 4, 5, 4, and this should be 3 then, yes? If that's a right angle triangle. And this is your x. Because sine is the opposite side divided by the hypotenuse, and this is 4 over 5. Of course, it might be 8 over 10. It might be, I don't know, 16 over 20, but at least one of them can be considered in this simple picture. So do you agree? Let me just take it away. If I ask you what is the sine of this angle in this particular right angle triangle, do you agree that you will give me the same number, 4 over 5? So this angle is actually your x. Okay, and then if this is 4, this is 5, this one would be 3. Okay? But what is my goal? My goal is to calculate the cosine of half of this angle. So what should I calculate? I need to calculate cosine of 1 over 2 of x. This is my goal. Yes? So this is my goal. So sine of x is 4 over 5. My goal is to calculate cosine of 1 over 2x. Do you agree? Because this, if instead of this one, if I put x, I am looking for this combination. I want to confirm that this is equal to 2 over square root of 5. So if I put that one x, I need to calculate this one. But it is not hard. Of course, you need to know a little bit of trigonometry, but can I calculate this? Let's see. Okay, so what can I write? Do you agree with me that I can write something like this? I can write cosine of x. Tell me why. It's equal to 2 cosine to the power of 2 x over 2 minus 1. Do you agree with this relation? This relation is this formula. Do you remember double angle formula for sine? It was 2 nu. It was 2 sine nu cosine nu. That is an extremely important combination, even if you don't remember the full detail, but you need to remember this combination is famous. Another famous combination, if you remember, comes from cosine of 2. We studied that. It becomes 2 cosine squared nu minus 1. Yes? But now look, instead of nu, you can replace it with x over 2 in the second equation. Then 2 times nu becomes x. Yes? And then instead of nu, I am putting x over 2. Do you agree? This relation is actually the formula that you have studied in chapter 2. But I am just replacing the angle with x over 2, and I get this. And now you see my question mark is here. But do I know cosine? Yes, because sine is 4 over 5, so cosine is the adjacent side divided by that. So this becomes 3 over 5. And let me move 1 to the right. It becomes plus 1 is equal to 2 cosine squared x over 2. And then if I add them, it becomes 8 over 5 is equal to 2 cosine squared x over 2. And then I divide by 2, it becomes 4 over 5 is equal to cosine to the power of 2 x over 2. And then I take the square root. But do I need to put plus and minus? Here, no. Yes? Why no? Because x is an acute angle. X over 2 is also an acute angle. The cosine of the acute angle cannot be negative. And I get cosine x over 2 is 2 over square root of 5. And that is the calculation in our world, not in the complex system. Yes? So we were also able to confirm that using just real numbers. Yes? But there are problems that we actually don't have any solutions for them in the set of real numbers. Okay, especially calculating very hard integrals. So there are integrals that we cannot use the method of real numbers to calculate them. Here, at least, you get a flavor that how complex numbers can be handy if I want to do something in the real system, in the real numbers, yes? But at least I immediately show you another alternative, which is in this case much simpler even, yes? In principle, assume that you have know the formulas, everything in your head, you can calculate it much easier. than this one. It's more straightforward to come to your brain. But there are many problems that we cannot solve them just using the analysis of real numbers. Okay, so then we use some tricks to calculate them using the complex numbers. So that is actually, this is a very valuable tool at the level of mathematics. And if you remember the first session, I told you that this I appears in the Schrödinger equation, which is supposed to describe the behavior of an electron. And if you take that I away, the prediction becomes wrong. So I don't know, even in the world of physics, probably complex numbers are not that imaginary, because if you take them away. But in this sense, they are still always imaginary. It is not possible to measure something in the laboratory and then you get a complex number. Whenever you measure something, you get a real number out of it. Okay? Anyway, so is that understandable? So remember this trick. There is no exam for this, but this is in future. It's very, very important for you. The complex numbers is extremely important if you want to continue something related to mathematics. Is that clear now? Okay, so we have a little bit of time. So let me give you an equation to solve. Okay, so before do that, let me finalize this lesson. This is not in this form in the book, but everything you need is in the book. So let me just formalize it in this way. So let me define it for you. So definition. So let Z be a complex number and let N be a real, a natural number. And be careful about this article I am using. And nth root of Z is an nth root of Z is a complex number. Is a complex number W such that, okay, can you complete it for me? Just read the text again. Let Z be a complex number and let N be a natural number. And nth root of Z is a complex number W such that what happens? What is the meaning of the third root of, yes?
W to then C.
Yes. But when you say what is the meaning of the fifth root of 7, it is a number so that when you raise it to power 5, it becomes 7. So when I say an nth root of Z is W, it means that W to power N becomes Z. This is the meaning of the nth root, of an nth root, yes? When I say that W is an nth root of a complex number, it means that if you raise this W to power N, it becomes Z. Yes? Is that understandable or not? For example, when I tell you that what is the meaning of the fifth root of 7, this means that a number that if I raise it to power 5, it becomes 7. This is called the fifth root of 7. The reason is that when I raise it to power 5, it becomes 7. Yes? That's the idea, the same. But the notion of nth root in complex numbers is more complicated. Can you see why? Why it should be more complicated than in the case of real numbers?
Because there can be more than 2 answers.
More than 2 answers, yes? In the set of real numbers, we have 2 scenarios. If our n is even, so if, for example, if I am just solving this equation, and I ask you to find x, you would say x is the third root of 5, and there is only one of them, and that is this number. If I want you to solve this equation, what happens? It becomes plus or minus the second root of 5. And by convention, when I say that you write this symbol, I mean always the positive one. So I need just one convention, yes? Yeah, here I don't need any conventions because there is exactly one if this is odd. But if there is even, there's always two of them, which are opposite of each other. And then if I ask you what is the meaning of the second root of 4, we always say that in principle there are two numbers, but by convention this is the positive one always. Yes? But the scenario in complex numbers becomes harder, yes? Because if I want to solve this, there are 3 roots, not 1. And if I want to solve this, there are 2 roots. If I want to solve this one, how many of them are there? There are 4 of them. And they don't just differ by a minus sign. They differ different. They are located in different points. Yes? So it means that we need, this is a little bit harder. But we can immediately solve this problem once for all. Okay? How can I calculate this? Using the method of this polar coordinates. So, sorry, polar form. So I would say that let W be R cosine theta plus I sine theta. My goal is to calculate W, okay? I put it back into this equation, and I use the same trick, actually. So it becomes n theta plus I sine n theta is equal to Z. So what is my goal? My goal is to find the formula for all possible W's so that when I raise them to power n, it becomes equal to Z. So I am just using the same trick, yes? I am assuming that W is this. I plug it back into this equation. It becomes this. And now can you tell me what should I do after that? It's very similar to what we actually started today. What should I do? Yes?
Calculate R.
The absolute value.
Yeah.
What is the absolute value of the left-hand side? R to the n. What is the absolute value of the right-hand side? Yes?
We don't know yet.
Yeah, we know that because Z is given. Yeah. In principle, what I don't have any other formulas for that. I just write absolute value. And then I am looking for R. So what is R? The nth root of absolute value of Z. But this nth root is being calculated in the set of real numbers because R is not only real but positive. Okay, so this is the absolute value of this number that I am looking for. Be careful. I give you Z, I give you N, you are supposed to calculate for me W. Yes? So you don't say that this is I don't know. Yes, you know, because if I give you Z, you know the absolute value of Z. And if I give you n, you know the nth root, so you calculate this one for me. So R is known. I want to look for a formula. Yes? So I'll have to solve it algebraically. Okay, and then what I have to do, I have to plug this back into this equation. So I have to plug this back into that equation, but then here, I need to be a little bit, so do you remember, if I put it back into this equation, I want to compare the left-hand side with the right-hand side, yes? So this means that I have to write this one in the polar form, and that was your idea when you talked about it. So I would say that let Z be equal to, how can I write in polar form? I would say absolute value of Z times cosine. Instead of angle, I just write argument of Z. Whatever it is, we don't know. Because I'm looking for a formula. This is a little bit abstract, but I don't think it is beyond your math knowledge. Yes, do you understand if I write something like that? Because when I write Z, I have to write R, which is absolute value, and I have to write theta, which is the argument. But because I have only Z, I have to express everything in terms of Z. So that would be the Z in polar form, yes? And now compare them. If I put this back into this equation, what happens? This becomes absolute value of Z times cosine of n theta plus I sine n theta is equal to absolute value of Z cosine of the argument of Z plus I sine of argument of Z. Yes? And then what happens? This absolute value of Z and this absolute value of Z are gone. And then I can conclude that cosine of n theta is equal to cosine of the argument of z, and the sine of n theta is the sine of the argument of z. Yes? And then what can I conclude from here? I can conclude n theta is nothing except argument of z. Plus, of course, 2k pi. And k goes from 0 up to, by that rule of thumb, up to this one. So theta is argument of z divided by n plus the 2k pi divided by n. K goes from 0, 1 up to n minus 1. I just finished a little bit from now. Is the calculations clear? I'm just doing the same, more or less the same thing, but written it in algebraic form. So I was trying to look for theta and I got it. Yes? Okay, so what we can say? We can say that if w to the power of n is equal to z, I got my formula. So w is equal to the nth root of the absolute value of z, and then cosine theta, which is that number. So it becomes argument of z. Let me combine them. 2k pi over n plus I sine argument of z plus 2k pi divided by n, where k is 0, 1, 2, up to n minus 1. So this is your formula. Okay. So in the book, probably they just want you to learn it all the time. So they haven't provided you with this formula. So if you remember, from case to case, I have to repeat the same process over and over again because they want you to learn this process. But if you're confident that you'll learn this process, and this is your formula. So whenever I give you an equation like that and I ask you to find W for me, this is your formula. Yes? And then you need to know that K goes from 0, 1 to up to 1 unit less. If I ask you how many numbers you see here, you would say there are n numbers. Okay? So keep this formula. I will try to use this formula in the next session on Friday. Yes? But I think it's understandable, isn't it? Yes? I've just done the same process, but instead of working with numbers, I am working in algebraic form to get a formula at the end. And we got this formula. Okay, we will explore the consequences of this formula in the next session. Thank you very much.
Thank you so much.
Thank you. So I end this stream here.